Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Fundamentals of Least Squares. Least squares regression is a method used to find the curve, i.e., a model, that best fits a set of data points. The goal is to minimize the sum of the square differences between the observed values, i.e., actual data points, and the values predicted by the model. Squaring the residuals ensures that both positive and negative deviations from the model are treated equally, i.e., no cancellation of errors. This is a convenient method that produces a smooth, continuous function which can be optimized using calculus. Least squares regression is applied in data analysis, modeling, prediction, etc. Suppose a set of experimentally derived data for a continuum is to be linear. Nevertheless, the data points, which should ideally correspond to points on the straight line, exhibit deviations from a linear relationship. Such deviations, or scatter, are called noise. A prediction curve can be constructed with, for instance, a Lagrange interpolation polynomial to represent the data with an interpolating polynomial. But a high-order Lagrange interpolating polynomial will pass through all data points, including the data tainted by the noise, as shown. As a result, the prediction curve will also contain noise, and the predictions will be unreliable. The least squares regression is generally used to generate a curve fit that is free from existing noise in the raw data. The principle of least squares regression is to minimize the difference between the predicted and measured or observed values, and so we define the error as the difference between the observed and predicted values. Common regression models can be categorized as follows. 1. Linear model is encountered in many fields of science and engineering. 2. Polynomial models can be used with almost all data. 3. Nonlinear models can be viewed in two categories, linearizable and nonlinearizable models. The linearizable models include exponential, power, saturation growth, or decay models, etc. Most models are nonlinearizable models, which require solving nonlinear set of equations. The principle of least squares regression is to minimize the difference between the predicted and measured or observed values. The sum of the squares of residuals, SSR, is the objective function defined as follows, where n is the number of measurements, observations, or sample size. For a suitable model, the model parameters A0, A1, A2, etc. are found by minimizing sum of the squares residual e, which is a function of model parameters. This is done by taking the partial derivatives of e with respect to a's and then setting them to 0. The resulting system of equations, which can be linear or nonlinear, is solved for the model parameters. The critical first step in least squares requires determining the most suitable model for the dataset. The physical event and relationship suggested by the theory is undoubtedly the first thing to look at when adopting a best fit model. Any set of observed data can always be fitted into a polynomial. If this route is to be taken, we must ask, what should the degree of the polynomial be? We should plot the observed data and determine the best fit model, or the degree of the polynomial by visual inspection. The data in the figure on the left is suitable to a second or higher degree polynomial, and the data on the right is suitable to a third or higher degree polynomial. Once the model constants are determined by using the least squares method, we seek answers to the following questions. How well does this best model represent the data? How good will the estimates from this model be? Can the model be further improved? And so on. A visual aid in terms of the suitability of the model to the data is not sufficient. a measurable quantitative criterion is required to measure the goodness of fit. The sum of the squares of the residuals of the observed data is minimum owing to the minimization requirement, and it should be 0 for any data that is completely free of noise. The sum of the squares of the mean deviation, which is a measure of how much the data deviates from the mean value, is computed from the following expression, where y bar is the arithmetic average of y's. This quantity does not become 0 even for an ideal curve fit. R-squared is a quantitative metric for assessing the goodness of a regression, and it is defined in terms of SSR and SSMD as follows. The R-squared is also referred to as the coefficient of determination, and R is termed the correlation coefficient. Ideally, R-squared should be calculated and interpreted as it provides a measure for the strength of the relationship between the dependent and independent variables. In a set of data, a correlation between the independent variable and the observed variables may or may not exist. If a functional relationship can be established between two or more variables, it can be said that there is a correlation between the dependent and independent variables. In Figure A, the data is scattered all over, so there is no correlation between X and Y. In Figure B, the data scattered about a line with large deviations depicts a weak correlation. As the deviations get smaller, as seen in Figures C and D, the strength of the correlation between X and Y increases. Pay attention to labeled R-squared values. R-squared, also, represents the percentage of the data close to the fit. A danger of relying solely on R-squared is that it can lead an analyst to misconclusions, especially when dealing with very few data points. Also, using a large data set or adding extra variables to the data set may also lead to elusive conclusions. When more data is added, R-squared does not decrease but rather increases, giving a false sense of confidence. To penalize adding extra variables, we use the adjusted R-squared, where n is the number of data points, k is the number of variables, including the model parameters or constants. Another quantitative metric for measuring the quality of the model fit is the rmse, stands for the root mean square error. A best fit curve, yx, estimates a prediction for any x, while the rmse measures the spread of y's. It is defined as follows. An alternative definition of our MSE is the standard deviation of residuals computed as follows. Our MSE equals 0, i.e., R equals 1, indicates that the measured data are 100% represented by the fitted or predicted model. Since our MSE is measured on the same scale and in the same units as Y, 68% of Y values should be within plus and minus our MSE. The data is represented by confidence intervals of 68% and 95%, plus and minus 2 times our MSE, around the best fit. The confidence interval band shrinks as R-squared increases. An assessment of the usefulness of a curve fit should start by examining the residuals via the residual plots that reveal the effectiveness and reliability of the model adopted. Residuals provide qualitative information about the goodness of the fit. Note that the observed data points are gathered along the best fit line. The residual plot depicts, relative to Y data, small deviations and unbiased distribution of the dataset. The residual data is termed homoscedastic if the variance is constant or depicts homogeneous scatter. For unbiased and homoscedastic data, the residuals are randomly scattered around the E equals 0 line, and the average of the residuals is 0 in each thin vertical band. The residuals in a biased and homoscedastic case may yield a linear pattern, which is most likely due to an independent variable that was overlooked or not taken into account in the experiment. The residuals in this case form a quadratic pattern, which is indicative of a nonlinear relationship. In other words, a linear relationship is forced onto nonlinear data. A linearization, i.e., transformation, of the data might help mitigate this type of problem. In heteroscedastic data, the variance of the residuals increases or decreases along the horizontal axis. In an unbiased heteroscedastic case, while the average of the residuals yields 0 for every thin vertical band, the variance increases from the left of the plot to the right. In the figures, biased and heteroscedastic linear and quadratic patterns are illustrated. These patterns are also signs of trouble owing to using an unsuitable regression model. Predicted versus observed or PO plots provide qualitative and quantitative information about the regression models. When assessing the multi-regression models, the residual plots are impractical. Instead, PO values can be plotted, uppercase Y's on the horizontal and the lowercase y's on the vertical axis. The slope and intercept of the PO line describe the model consistency and the model bias, respectively. For identical observations or predictions, the resulting PO plot should be perfectly aligned on the diagonal, i.e., the y equals uppercase Y line and our rmse equals 0. Likewise, having data points close to the diagonal line, our rmse is approximately 0, indicates a reasonably good fit of the overall data. The data points spread closely about the diagonal lines of a linear model fit, and its PO plot indicate that the predicted and observed data are correlated. The unit slope validates the linear relationship between lowercase y and an uppercase Y, that is, the linear regression model is suitable for the data. In the nonlinear model and its PO plot, the deviation of the slope from unity reflects a relative scaling factor between the two sets. The model bias, shift, is determined by regressing the PO values onto a straight line and comparing the slope and intercept of the best fit line against the diagonal line. Note that the R-squared values for nonlinear regression and the linear regression for the PO data are not the same. The advantages of least squares regression are: least squares regression is an effective tool for numerical analysts. Estimated model parameters are the optimal values. When a model compatible with the theory is used, a very good result can be obtained even with a relatively small amount of data. Regression allows important physical parameters, slope, intercept, etc., to be determined. The theory of computing confidence intervals, predictions, goodness of fit, and so on is well established. Numerous software programs are available, allowing the use of a broad range of single or multi-regression models. The disadvantages of least square regression are: regression models can justifiably be used within the range of data. Hence, they have poor extrapolation properties. The procedure can be sensitive to outliers or some data anomalies. The data is assumed to be suitable for the adopted regression model. Overfitting can be a major issue when using polynomial models. Nonlinear models may require iterative techniques to solve the system of nonlinear equations. With this note, we conclude this session. That is all for now. See you next time with another topic. Bye.